As I mentioned last week, though, today we're going to be closing out what we've been working on as far as dealing with rates of change, which led to us going into the perspective of differentiation on Friday. So today we're going to look at that. We'll start with the limit definition of derivative, but we're going to work our way into the derivative rules. Okay. Now, what you're going to find is some of this stuff is not necessarily going to be covered on this first test. We definitely want to know the definition, the limit definition of derivative. But some of these differentiation rules will help you make sure you're getting to the correct result. But we're going to dive more into it next week. Okay. As it stands this week, we're going to have a review day on Wednesday. So make sure you're studying and come with questions then, because the questions you have will kind of drive that review session. And then Friday is our exam. Okay. Any questions before we get started? Now, as far as it, as I said, there's still a couple of you, as I mentioned, that have not put your first and last name in the chat. Is everyone able to hear me?
Yes.
Yes.
All right. So if you could hear me, make sure to get our first and last name in the chat if you have not done so yet. With that said, let's move forward. This first problem here, I want us to differentiate the given function. So f of x equals 9 minus x squared. The way that we want to handle this differentiation, though, so let's go through the limit definition of the derivative. All right. So make sure you remember here as we deal with this, the limit definition was f prime of x, which is our derivative notation of a function, equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So the limit as h approaches 0 of that difference quotient, right? The transition from average rate of change to an instantaneous rate of change. So make sure you see here, doing the limit definition, we're going to have to go look in and find that piece that we've been looking at, which is the f of x plus h here. We don't have that, so let's go get that first. Now I'm going to multiply out that binomial, the x plus h times x plus h. So make sure you see there where I'm getting that stuff from. Dealing with this though, make sure you see I left it in parentheses because now we're going to have to distribute that negative. That's one thing you want to be careful of here with some of these problems, as we've talked about. Always watch your signs. That is definitely something that can get in the way of accidentally forgetting it or something along those lines. All right, so now we have f of x plus h simplified. We can go back to the process of dealing with the limit and the difference quotient. Are there any questions with this before we move forward? All right, so shrinking this down a little bit, moving over. We can go into the whole process now. Make sure you see here that when I wrote this out, we're subtracting the entire function. All right, so I distributed the negative to the 9 as well as the x squared. So make sure you see both of those signs change there. All right, going back to this subtraction. The other thing that we talked about that we definitely want to watch for as we go through this is recognize that several of these terms are going to go to 0 oftentimes when we're dealing with polynomials. Okay, so when we deal with a quadratic or linear or any other polynomial, hey, I should expect some terms to go to 0. When you start dealing with other functions, it changes a little bit. Remember, when we have fractions involved, we get a complex fraction situation like 1 over x plus h minus 1 over x all over h. Remember, this is where we talked about multiplying the top and bottom by the common denominator. This is definitely one thing to watch for as you're dealing with this. And hey, whatever I do at the top, I do the bottom. Just remember to distribute this. Okay. We also looked at radicals and how you have to rationalize before. So make sure you go over your notes and do the homework. And if you have questions, make sure you bring those up with me, whether it's in my office hours or coming to class Wednesday with that review. Okay. The nice thing about this though is once we get that taken care of, when we do deal with this limit, everything that's left in the numerator right now has an H on it. So that will allow us to divide out an H off of each term. And we can now evaluate this limit through direct substitution, which will give us negative 2x. The idea here is, hey, I had H in the denominator here, so I can't plug in 0 yet because that'll give me a 0 in the denominator. Once I divide out the H, though, I no longer have the fraction. So make sure you see like, hey, I could put in 0 here, and then all I'm going to have left over is the negative 2x. What we find then is through the limit definition is that, hey, I had a function, and the derivative of that function is negative 2x. As we talked about Fridays, this is looking at a continuous function over its entire domain here, because we're working with quadratic, to where I can go in and say, hey, f prime of negative 3 will give me positive 6. Well, what does that mean? Well, that means the slope of the tangent line at that value is going to be 6. Now, keep in mind that's at x equals negative 3. So I could plug in an x value and I can get the instantaneous rate of change at that point. I don't have to go through this every time, this whole process, each and every time with each different x value. I can do it all at one time and then get all the values I need. Okay. Any questions with this I help some feel better about?
Can I see what's written behind you? Like where you at?
Sorry. Does that help?
Yes, sir. Thank you.
Any other questions? All right. So like I said, this was just making sure we reviewed the limit definition of derivative, going through that process. Okay. But the reason we definitely want to have this is to focus on the fact that, hey, this is giving me the instantaneous rate of change on a function over a given domain, right? Now, keep in mind the domain definitely has to be continuous. So when we deal with the quadratic, hey, it's continuous for all real numbers. So that's one of the nice things about it, okay? With that in mind, though, make sure you see here that this negative 2 didn't come from nowhere, right? We didn't just make up a 2 out of just thin air. There was a 2 within the problem because it was x squared. So that's going to be the next step we look at, the patterns that we can begin to connect. So continuing with that, all right, we're going to introduce two things. First, the notation of taking derivative of a function or expression, all right? And the next step is this thing we call the power rule. All right, what you're going to see here is anytime we have a term that just has a constant for its exponent, we can take the derivative by bringing that constant down in front as a coefficient. So you'll see this 2 moves to the coefficient. And then we'll take that existing exponent and we'll subtract 1. Well, the thing with quadratics is that when you subtract 1, you get to an exponent of 1, which we just put x. So that's why we saw there we didn't really put an exponent of 1 on the previous problem. So what we'll see here is if we look at these other examples I could have a positive exponent, x to the 7th. Instead of having to go through that whole process of the limit definition of derivative, we can trust that what we just did is going to stay to a consistent pattern. With that pattern, what we'll find here is that I'll write this as 7 times x, and then my new exponent will be 7 minus 1. So I bring down my exponent that existed to a coefficient, and I dropped that exponent that was existing by 1 degree. So instead of 7, when we're done, we should have 7x to the 6th. What we have here is x to the 7th would be our function that we started with. When we're done, that is going to represent the derivative of that function. Now, what you'll see here is this notation is going to, this is the idea of Leibniz notation. And if you remember the other day, I talked about how we went from using delta y over delta x as an average rate of change. But now we're looking at it through the perspective of a limit that says, what if that difference in x is so small, it can't be differentiated between itself and 0? That's going to allow us to bring in the differentials, dy dx. All right, this is a shorthand notation where this is a function which like y equals x to the 7th. That's why we like function notation. So make sure you remember that and y are interchangeable. Any questions here? I clear up with this first one before we do the second one? Now, what you're going to see here is that you can have different setups as far as dealing with your exponents. As long as it's a number, a real number, we can follow this pattern. With this next one, we have a -3. So what we'll see is the -3 becomes the coefficient. But remember, this is where we're going to go to that -3 and we're going to subtract 1. Definitely want to be careful here because -3 minus 1 is going to make that -4. Any questions with the second one here or the first one?
Mr. Green,
Yep.
I don't really quite understand the idea. Can you repeat it just one more time?
All right. So what you're seeing here is we're trying not to have to go through this every single time we deal with something. That's the whole point here. Okay. Now keep in mind, this had 2 terms on it. So using the limit definition to handle both terms. We're going to talk about the constant term in a second. What we focused on was this first term. All right. What you'll see here, it went from -x squared to its derivative being -2x. Well, this pattern, as long as you have a real number k, will follow for any exponent. So that's what this is saying here. For any real number as an exponent, if I wanted to make it up, we could say x to the pi as a real number, so we're good there. You could do x to the -√3. Don't see it all the time, but that's still a real number. Okay, so please keep that in mind first and foremost. With that in place, though, we can follow the pattern that we just saw. The exponent becomes the coefficient. All right, and then we subtract 1 from the existing exponent. This will give us the derivative of that term. All right, so that's why we call it a power rule. Those we're looking at exponents. But whenever we want the derivative of a term that has a real number exponent, we can follow this with each of these problems. So you'll see here the 2 became an exponent. The 7 became, not an exponent, sorry, became a coefficient. The 7 became a coefficient. This -3 became a coefficient. Our point of doing this, though, again, is to go from the term we have to its derivative. So make sure you see that the result here is the derivative of that term. Now, that's why I wrote off to the side here. Make sure you see we could call that its own function. G of x equals x to the 7th. The result that we have here is the derivative of that, 7x to the 6th. Now, if you wanted to, you can go through and try to prove this using the limit definition, but know that that's going to get a little tedious. So if you had the limit as h approaches 0 of x plus h to the k minus x to the k all over h, you're going to have to go in and talk about how the world do we deal with this. Okay, so that's where something becomes, hey, there might be a way to deal with that, but we would need a little bit further and more depth of understanding with the algebra, the calculus, and way we deal with stuff. So please keep in mind that that's one of the reasons we don't do that. Even if I change this to a 7, it's still tedious. Now, this one I could better explain to you. As you remember, we looked at x plus h squared being righted twice. Imagine having to write it 7 times. So that's why we want to start trusting these rules that I'm presenting to you. So hopefully that helps you better see that, like, hey, instead of having to do all that and multiply something out 7 times, we have a better way to handle it. This is also nice because what do you do with -3? Or what if I put a pi there? What if we did x to the pi? Well, hey, I could follow this rule that we have in place. Does that help?
Yes, sir. Thank you.
Now, no problem. Now understand, this is for different types of terms that just have a real number as an exponent. So keep that in mind. This is just us looking at individual terms right now. We're trying to simplify it a little bit. The next one then is, well, that other problem had 9 minus x squared. What do we do with constant values? So make sure you see here, well, we have a rule for that as well. Is the screen clear on your end? Or is it blurry for y'all?
It's clear.
Yeah, I can
All right.
see it.
Just making sure. Now, with that said here, make sure you see that as we look at this, this is going to be the derivative rule for constants. The idea here is if I look at a graph of a constant, let's just say y equals 3. If I go graph this, it would look something like this. No matter what 2 points I pick on this line, there is no change up or down. There is a change left to right, but nothing changes up or down. So the slope of this would always be 0. So whenever we look at this from a derivative perspective, we can take that kind of understanding of slope, like, hey, the slope of a horizontal line is 0. Well, the derivative of a constant term will be 0. So when I go down here and look at -50, hey, that's a constant term. No variables attached to this in any way. The derivative of this, because it's a constant value, is going to be 0. It can be pi. The derivative of that is 0. As we look at that previous one, we looked at d dx of 9. Hey, the derivative of that is 0. All right. And make sure you keep in mind, it's like thinking of it like a horizontal line, the idea of the slope of that being 0, because that's what we focus on when we're doing derivatives is rates of change. Any questions with these? Now, I may have not said it directly, but make sure you see here with this e, that's a constant value. It's not a variable. All right, so moving on to the next one then is what happens when we start mixing these. This is definitely one of the important parts that we want to make sure to look at. We looked at 2 different perspectives, power rule and dealing with constant values. Well, you'll see here, the first one here at the top is going to deal with a constant multiple. So if you remember with limits, if we had a limit of something where it's like you could factor out a 2, well, I could just put the 2 in front of the limit and then deal with it. That was one of the things I looked at from the limits property. So you'll see, hey, that still holds true because if it worked with limits, it's going to work with this. So the definition or the proof of these things would go back to the limit perspective. So please keep in mind, like, hey, if I could factor out a constant term, I can just kind of get it out of the way. The sum or difference rules, well, just like we saw with the limits, they're going to apply here as well. So you'll see with my example, if we have the derivative of 2x minus 5, the first thing I do is I break it down into the 2 separate terms. Derivative of 2x minus the derivative of the 5. We can go even another step here and say, hey, that 2 I can just pull out because it's just a constant multiple. It was a coefficient on the x. And what you'll see here is now we can say, hey, what's the derivative of this x value here? Well, when we look at the x value here, I brought the exponent out in front. So make sure you see that if you have just x, the exponent that existing is 1. So when we do the derivative of that term, using the power rule, we bring the 1 down and we multiply by 1 minus 1. So that's where this 0 is coming from here. Now, the important part to remember with that is anything to an exponent of 0 is 1. So that's where you're getting this 2 from, because 2 times 1, so 2 times 1 equals 2, minus 0 is still 2. Now, to give us an example to work on, let's go back to our first one we looked at, right? So we had what? 9 minus x squared. So f of x was equal to 9 minus x squared. And we want to find the derivative of this. So the derivative of f of x will equal the derivative. I keep putting the x for show, sorry. Of 9 minus x squared. Well, based on what we just wrote, we can go through and break this down differently. Let me get to a new page. So the derivative function of f is going to equal the derivative of 9 minus x squared. Breaking it down the way we just saw, we could put the derivative of 9 minus the derivative of x squared. Well, the derivative of 9, that's a constant value. So the rate of change of the constant value is 0. Over here, we have x squared. So what I need to do then, from here to its derivative, I bring the exponent, which was 2, and I multiply it with the x, and the new exponent is found by subtracting 1. This will give us minus 2x to the first, or negative 2x when we're done. Now, keep in mind, as you're writing out your work here, it begins to be very important that you keep in track of what you're writing down. This function is not the same as my original function. Our notation matters a lot. And if you just come down this list and start putting equal signs without taking note of your notation, you're going to try to say that these are the same, and they're not the same. So that's why it's very important to make sure to state, hey, what I'm working with now is not the function that I started with, but the derivative of that function. This new function, as mentioned, whenever I plug in an x value, I'll get the rate of change at that point. So like if we pick x equals to 2, we could plug it into the original function and we'll get what? 9 minus 4, which is 5. So that would be the point that's on the graph of the original function. But when we plug it into the derivative function, we get negative 4. Well, hey, that's the slope of the tangent line that goes through the 0.25. Okay, so make sure you see the difference there. Any questions with connecting it back to that first function? All right. Well, here's another one then. So as we continue with this, I have a cubic function now, all right, dealing with real number exponents when we have polynomials. So this is definitely going to fall within our power rule and such. One thing I do want to point out, though, is if you start with g of x and we write this here, that's just another way of saying g prime of x. So make sure you're comfortable going in between the different notations. As I mentioned, another one that we'll start working with is like, oh, this can be written as y equals. So the derivative of y can be written in a more shortened form of dy dx, okay? So make sure you see the different notations that can come about. With that said, though, make sure you know that now I'm moving forward, not with my original function, but I'm trying to differentiate it. I want to focus on the instantaneous rate of change. Now, we could have gone back and used the limit definition of this. That's not something, though, that you want to do again. Please make sure that you look at the examples as you prepare for this first test and be like, okay, yeah, I can follow this pattern. I could expand upon it if we need to, but we don't need to. What I hope, like I said, with this and then starting next week, is to start building our knowledge and understanding of these rules. Make sure we remember them, use them properly, but make sure to see that not only does it save time, but it lets me get to something more quickly and concisely. Okay. With that said, the way that I would write this out at the moment would say, hey, Remember, I can go through and look at each term separately. Going through each term separately using the rules that we looked out, right? We could do stuff like for this first term, bring that coefficient out to front. It's just a constant multiple. We're only focused on taking the derivative of that x cubed. The second one, we could pull out the 5. And the last one, we're just going to leave the same. With that in place, though, make sure you see here that as we go through this, we're going to apply the power rule to this first term. So it'll be 2 times 3 times x squared minus 5 times x to the 0 plus 0. Make sure you remember here, anything to the 0 power is just 1. So one thing you'll find is that we can kind of add to our little list of rules if you want. Anytime I have the derivative of just x, that equals 1. You don't have to go through this every single time of saying, oh, that's x to the 0, which will be 1. Okay, so be careful with it. What you'll find that goes back to the linear term that's like, hey, technically, if this was a line, if we got rid of the cubic part, our derivative would have been just -5 because that would be the slope. Okay, so the same thing will hold true for a linear term. Even though the function is not a line, there's some turning taking place, specifically 2 turns at most. This is treated similarly, that when I'm done, hey, that's just going to be -5. Okay. So even now, I know I wrote out this in a few steps just to make sure to highlight and walk through the rules. What I hope that we get comfortable with is the fact that, like, hey, I can apply these rules without having to write them out. That is one thing we're going to work on next week. But as we go through here and clean this up, we'll find, hey, the derivative of g is going to be 6x squared minus 5. Now, the one thing I will say is we're looking at this. This is much nicer than having to do the limit definition, but make sure you follow the directions on this first test. Some of y'all may have taken this or another calculus class before. You need to follow what the directions tell you. So that's going to be one important thing that I would definitely highlight. Another thing that I would also point out is I added on Canvas a practice test for you. So make sure you check that out and let me know if you have any questions, concerns with some of those problems on there as well. Are there any questions with this problem though? Getting the derivative of g of x. All right, here's another one then. I want to differentiate this one real quick. All right, update the attendance. All right. So jumping into this problem here, make sure you see when I'm saying to differentiate or find the derivative of the function, we're going from h of x to now dealing with the derivative function of that. Now, as I go through here, make sure you see what we're eventually going to do is look at these as individual terms. So when we're dealing with this, make sure you find your addition and subtraction. Remember, hey, I'm looking at this at each term individually. This first term, make sure you see here, hey, I have a coefficient that's going to stay where it was, right? So the 7's just a constant multiple, keep it. What I want to do then is multiply this with the x squared, the derivative, sorry, of x squared. That'll give me 2, because that was the existing exponent, times x. All right. It's just x, though, because 2 minus 1 would just be the 1. The next one here would be 3 times just 1. The 3 being a coefficient, we leave it alone, but the derivative of x, as we just saw, it's always going to be 1. Lastly, we're just going to put the plus 0 here. Cleaning it up will give us the derivative we're looking for. So when we go to differentiate h of x here, we start with a quadratic, but we end up with a linear. Any questions with this one? I clear for somebody? Now, one thing I do want to point out here is understand that with that said, you might be able to take multiple derivatives. This could be a function that represents an object falling from somewhere, right? So when you think of a quadratic, we're thinking of that parabola shape, okay? So when I look at the instantaneous rate of change at a particular point, that could be kind of, the distance over time. So like we would say meters per second. At that point, we're dealing with kind of something dealing with velocity, right? Well, when we think about velocity, we can then talk about its rate of change, which would get us to acceleration. So understand as we deal with these functions, there might be times where we need to do a derivative of a derivative. So understand that since 14x minus 3 was a line, it's still a function. We can take the derivative of it. So hopefully what you see here is like, hey, if I go through and do that, I would just get 14 in this case. The negative 3 is a constant term. The derivative of that is 0. And as we saw with this linear term just giving us negative 3, this linear term would give us just 14 if we do another derivative, okay? Just know that it's always going to be determined on what you're trying to get to. The notation here, we would put as h double prime of x. So this would be the idea that we want to make sure to always read the notation you're working with. All right. For derivative notation, we'll use these dash marks to help highlight like, hey, as we're dealing with this, what derivative am I on? Okay. Now, right now, it's more about practicing the derivative. So I'm showing this to be like, hey, we can take a derivative of a derivative, but the same rules we applied up here to get down, we'll use to move forward. All right. Let's get another one. Now, I'm throwing up this new one here because now we're not dealing with something that may not be continuous over all the numbers. Okay, so this is definitely a situation where we have to be careful what we're working with. All right. The good news is most of the time you could just remind yourself like, hey, from the beginning, x cannot be 0. Make that known from the beginning. As long as we don't use 0, we'll be fine. Now, as we've talked about limits, we can go in and kind of discuss this, right? If we need to get further information, we could always do stuff like the limit as x approaches 0 from the left of our function, and the limit as x approaches 0 from the right of our function, and we can define what's going on there with around 0, okay? What we'll see here is it's going to be a vertical asymptote, So we should expect something like this going to point towards infinity or negative infinity for both of those, okay? But that's not the focus of this part, okay? So the main thing that I would say for this part is just acknowledge the fact that we can't use zero before we move forward. With that said, we didn't do anything that talked about fractions, okay? However, there's one way that you can handle fractions oftentimes that will allow you to get from a rational setup to something that follows the power rule instead. What you'll see here is take this fraction and break it up into several different fractions. So since our denominator was just x squared, let's break it up to where each term in the numerator is over x squared. Now we have three separate terms that share that common denominator. And the idea here is it's like if you had 5 over 3, we could write this as 5 plus 3 over 3, which would be 5 over 3 plus 3 over 3. I don't ask me why I wrote that. It's not 5 plus 3. It's 2 plus 3. Sorry. We're just breaking down a fraction into two fractions that had a common denominator, okay? The reason we like that with this problem, though, is, hey, we can actually do this division. Just remember your rules of exponents. So if you have x to the m over x to the n, hey, I can subtract the exponent on top with the exponent that's in the denominator. Going through that process, then, I would get f of x equals 2x, because 3 minus 2 is 1, minus 3, right? We're able to do x squared divided by x squared right now because we're not allowing x to be 0. That wouldn't work with this function. But for this last one, let's go ahead and write this using a negative exponent. All right, so anytime you have something in the denominator and there's no x up here for us to work with, this is where we can use negative exponents. So this is definitely another thing that we need to make sure to remember is that, hey, whenever I have a negative exponent, that just means 1 over whatever I had there. And this was 5 over that, so just make sure you keep the 5 in front. Any questions on how I changed the problem before we do the derivative? All right, so make sure you see then as we jump into here and I'm saying, hey, I want to find the derivative of this. It does not change now from what we were doing before. We're going to go through each individual term and talk about differentiating the term one step at a time. What you'll see here is because we were dealing with a rational function, now I just have something with a negative exponent involved. That's the one thing that you want to be careful to see here that, hey, I've made an adjustment because I'm not working with a polynomial. Now I'm working with something that is rational. Well, that didn't change the rule though, still the power rule. So this first thing, I'll just get 2. The derivative of x is 1, so that's just 2, minus 0. And then over here, be careful, it's plus 5, and then negative 2 times x to the negative 3. I bring down the existing exponent to the front, and then I subtract by 1 to get my new exponent. So it follows the same steps before, but make sure you see it's just bringing a negative value into this mix. So we have to be careful when we deal with that negative when we go to simplify this. So this would give us, when we're all said and done, 2 minus 10x to the negative 3. Which I'm fine at this point. We leave it like that. We'll deal with that later. But if you wanted to write it more like we saw at the beginning, we could be like 2 minus 10 over x cubed. Any questions or concerns with this one? All right. Now, hopefully what you see here, this is definitely something that, as I mentioned, may not be directly used on this first test. But say you're trying to deal with something where you need to limit definition of derivative. Hey, you can go through that process, but you should know like, hey, this is probably what I should expect to see when I'm all done. Right? You could always check your answers with it. So as you practice it this week, make sure you see that, hey, this isn't for nothing, right? We're putting these rules in place. And I'm going to start building on them more next week, but they definitely help you this week. Okay. Are there any questions though before we finish up today?
Thank you. It's all clear.
All right. Well, the one thing I'll say then as we finish up, remember Wednesday's a review session. You have to come with questions though. If you don't come with questions, it doesn't help me do anything with that. So if you have questions, make sure you bring them on Wednesday. I would encourage you to go look at that practice test today and tomorrow. You can take it as many times as you want. It's not for a grade. So even if you just open it to look at what's there, make sure you do that and come to class. I will be available from 8:30 until our class time for any questions. So if our 50-minute class is not enough for you, make sure you stop by beforehand. I'm using the math lab right before class on Monday, Wednesday, Friday. Okay. If you don't have any questions right now, though, make sure again to double check that your name was in the chat. If it is, have a good day and I'll see you on Wednesday.